Hey, my friends, we are finishing up our discussion today on GC. And I know that seems fast, right? One of the things that's making that happen so fast is that a good portion of the semester that we spent talking about chromatography fundamentals, basics, resolution, all that good stuff, we were talking about it in the context of liquid chromatography, but it all applies the exact same way that to GC as it does to LC. And so we didn't need to go through all that stuff. Really, all we needed to do was get a picture of how column chemistry is different in GC than it is in LC, and then we can kind of apply all the same fundamentals. Um, well, we saw that, and it turns out there's not a huge plethora of modes of GC that you do like there are modes of LC, and so it was a fairly concise topic to go over. Today, I want to kind of close out our GC discussion by talking about the instrumentation itself. And so we're going to start that by looking at the anatomy of a gas chromatograph. Remember, the chromatograph is the instrument. The chromatogram is the data that comes off that instrument. So here is what a GC instrument looks like. So you have some source of carrier gas, and it's usually, pardon my terrible artistic skills here, but it's usually a gas cylinder, right? So we'll call this a carrier gas source. Yeah, gas source. There are other ways that this is done. You see some instruments that have a nitrogen generator, and what that is something that literally distills nitrogen out of the air and then pumps it into your column. Most commonly, it's a gas cylinder. The flow of that gas cylinder is controlled by a regulator, which I'm trying to draw with my poor artistic skills there, right? So exactly as you would use any gas cylinder in your lab. Okay, so there's some lines that lead to a heated injector, which is very different to the 6-port injector. You interface with this heat injector using a syringe, so let's just draw that for completeness. That's a syringe. It's an injection syringe, so your sample is going to go in that. You're going to handle that thing manually. You're going to stab it into here and fire off your sample. Okay, so that heated injector is kind of a side chamber on top of what we're going to call our column oven. So your sample meets the column here. The column is generally, we've seen a picture of these GC columns, they're coiled up inside that oven, and it leaves the oven. Generally, everything cools down to room temperature after it's left the oven, or it cools down significantly compared to the temperature inside the oven before it meets a detector. Okay, so when we were doing LC, we had a diagram like this, and we went from input to output. We went through all the different parts, and then we came back and said, hey, here's the chemistry inside the column, the modes of LC. We've just finished up kind of a discussion of chemistry inside the GC column, so we're sort of doing this backwards. We started in here, now we're going to go back, we're going to go input to output. Not a lot to say here. Like I said, sometimes you have a nitrogen generator which produces nitrogen from room air, but generally you just have a gas cylinder and a regulator. We are going to talk about the heated injector. We're going to talk about the column oven, and we're going to talk about the detector. I want to start with the column oven because I had a crazy revelation yesterday. I'm not kidding. I like texted all of my chromatography friends, and I was like, "Oh my God, I think I've just uncovered a crazy fact. You have to verify me on this." And it turns out I think I was right. You're not going to be as excited as I am, I promise. Okay, so the column oven is a really simple piece of equipment. It's a benchtop, not bench tour, benchtop convection oven. I don't know if anybody here is into baking, if they know the difference between a standard oven and a convection oven. Convection oven has a fan in it to keep the air circulating really well. So the benchtop convection oven in a small package, that's why it's the benchtop, with an oversized fan in there. So imagine you take your convection oven in your kitchen and you blow that fan up to basically the size of the entire back wall of the oven, and you've got a GC oven as long as you can control those temperatures really precisely, right? More precisely than your kitchen oven usually does. Okay, so what was my crazy revelation? It's that I'm so excited about this because this is my favorite thing in the kitchen. A benchtop convection oven with an oversized fan. This is literally, it's equal. I'm like, you know what? It's even more than equal. It is defined as, right? It's the 3 bar defined as an air fryer, right? If any of you have picked up air fryers is the hot new kitchen accessory. I'm super into it. I make chicken wings this way. Um, this is literally all it is. It's like separation science invented the air fryer, uh, decades and decades before the rest of us caught on to it. So I'm on a mission now. I wish we were still meeting in person, guys. I wish we were still in class meeting in person because I am on this mission to cook chicken wings in a GC oven. And if we were still getting together in class, I would make chicken wings for the entire class in a GC oven. If that ever does happen, if I ever meet my objective of doing that, I will at very least put it on YouTube and make sure you guys can see it. But okay, so that was the thing I was super excited about yesterday. But there's a reason for this. Let's just be clear. Why do we use a convection oven? Why do we have this giant fan? The giant fan is used to keep, the same reason, by the way, it's used in an air fryer, the same reason it's used in your convection oven if you use one for baking, to keep temps uniform everywhere. You want a nice uniform temperature of your column in every portion of your column, right? So you want a nice uniform temperature environment. But it also does a second really important thing that's less important for air frying, less important for baking cookies. It allows fast temperature changes. And that is important. Fast temperature changes are important because, and we've talked about this in the past, but I'm going to reiterate it here, temperature programming, or it's also called temperature gradients. This is the equivalent to gradient elution in LC. Right? In LC, we have gradient elution. In GC, we get temperature programming or temperature gradients. Works exactly the same way. You can have a step gradient, right? You can have a linear gradient. You can do things isothermal, which is the same concept as isocratic. And you do it for the exact same reason. You have the general elution problem, things that bind to the column too strongly, they have too high of a lowercase k, right, a retention factor. And you want them off the column faster because you don't get a lot of useful chromatography with too high of a K value. And so you do things like ramping the temperature in a linear fashion to get everything off the column faster. So rather than a stronger mobile phase, because as we said, the carrier gas, the mobile phase in GC, doesn't play an extraction component, so you can't make it stronger. The difference, the thing that you do is you make the temperature less favorable for adsorption on the column, and stuff comes off the column. All right, that's everything I want to say about the column oven. Just be as excited as I am that a column oven is actually just an air fryer. Really nice, fancy, precise one that you can control temperature really well on, but that's literally all it is. Okay, a little bit more complex than an air fryer is the heated injector. So let's take a look at the injector in GC, and it is very different to the injector in LC. In LC, remember, we had the 6-port injector. In GC, we have a slightly different task, and that task is related to getting a very small volume of sample onto the column. So I'm going to try and sketch this thing out. It's a little bit complex, and so I'm sure I'm going to make some mistakes here, but basically, actually, I've made my first mistake. I don't want to start there. I want a little bit of headroom. There we go. So picture a chamber. Looks something like that. Chamber with an inlet and an outlet. That chamber is a stainless steel kind of block, basically. So this is all stainless steel. This is a heated stainless steel block. That heated stainless steel block is lined in the inside here with a glass tube. So this is like a little glass lined compartment we'll call it a glass liner. We're looking at this thing in cross section, right? And so if we had sort of a stainless steel cylinder and you put a tube in the middle and you cut it down the middle, the walls would look like they were made of glass. So the glass liner, we have this glass lined chamber. Our carrier gas is entering this way. And we have at the top here, trying to draw a thick box, there we go. We have a rubber septum. So this is something that is sealed, and you can stab a needle through this thing and it'll remain sealed around the needle, right? So it's a rubber septum. Okay, carrier gas comes in here. Our sample, we said, was injected by syringe. So here's a syringe. There it is. Let's give it some gradations so that we know that that's what it is. Okay, so that syringe can be, let's call that our sample syringe, can be stabbed, for lack of a better word, through that rubber septum and enters this sealed compartment here where carrier gas is running over it. Heated stainless steel block. It's generally heated to above the temperature of the column. We'll talk a little bit more about that in a minute. And there's an outlet here. That outlet goes to a valve. This is going to be called the split valve, which just leads to waste. There's one thing missing, and that one thing missing is that our column connects like that. So that's our column. Okay, so I think I got all the bases covered here. Let me just check. Yep. Okay, so we're gonna call this area in here the vaporization chamber, right? The glass-lined vaporization chamber. Our sample is gonna be in some kind of volatile solvent. And obviously the molecules need to be somewhat volatile to be separated by GC. And what happens is, if you imagine basically, let's imagine, we'll talk about the split valve in just a few minutes, but let's imagine that thing's closed. Carrier gas is coming in here. Its only exit from this chamber is through the column and out to atmosphere at the end of the column. So if we rapidly eject all of the sample out of the syringe into this heated chamber, it will, because this is heated to a pretty high temperature, higher generally than the temperature of the column, by the way. That's an important detail we'll get to. Everything vaporizes really fast. Flash vaporizes is what they call it. Everything flash vaporizes inside this vaporization chamber. The walls are lined with glass basically to make them inert so that we don't get a lot of carryover from sample to sample. But the idea is, we've just injected sample, the carrier gas will push that vapor into the column. That's the simplest way to think about it. That's something called a splitless injection, and it turns out it's not the most common way of doing it, but it's the simplest way to see how this thing works. So we'll talk about split and splitless injections in a second here. Let's talk about one detail that I've mentioned a couple times now, the temperature of the injector, we'll call it T sub INJ, is generally much larger or somewhat larger, tens to 100 degrees higher than the temperature of the column. There's a couple reasons for this. High temperature, first of all, regardless of relative to the column, a high temperature allows sample solutions, because that is generally how we handle these things, as liquids at room temperature and pressure. Sample solutions to flash vaporize or all become vapor very, very quickly. But the lower column temp allows analytes to re-condense at the head of the column. Head of the column meaning the early part of the column. And so you get all of that sample onto the column, but you quickly, because the column temperature is cooler, everything gets condensed onto the column, and you start doing your extraction or your condensation chromatography pretty quickly, right? You're not sending vapor all the way into the column before it's starting to adsorb to the stationary phase. Okay, so let's talk about this split versus splitless thing and why we do it. So here's the challenge. We've talked a lot about open tubular GC columns and all the benefits of working open tubular, right? You basically get rid of your A term and you get better peak efficiency when you're working open tubular. The problem here is that the diameters are typically pretty small. That's actually a requirement of doing open tubular. You need to be able to diffuse to the wall pretty rapidly, so you have small dimensions of the tube. So the diameters are typically pretty small. We'll say on the order of like 100 to 500 microns as an inner diameter in an open tubular JC column. And what that means is that, if the diameter of this column is small, then any appreciable volume, let's say, a few microliters, they'll actually take up a long length, right? Because the volume is going to be pretty small inside there. So you put a big volume in there, it's going to take up a huge length of your column. You don't want that. You want to start with a plug-like, with a infinitely narrow sample plug. There's a reason for this. There's a numerical reason for this. We talked about extra column band broadening, right? One of those terms was sigma injector. The band broadening associated with how big your sample plug is. You want that sample plug to be as small as possible so that you minimize that sigma injector. But if you inject a large volume onto this thing, you're going to get a really long sample plug. So you're going to kind of erode some of your performance that way. So in order to get what would be here, I'm going to kind of approximate this. You want something, some small fraction, right? Some small percent, 1%, 2% of the length of the column to be occupied by your sample when you inject it. Maybe less, maybe even less than 1 or 2%. So in order to do that on a very narrow column, this requires very small sample volumes. By very small, I'm talking on the order of low nanoliter volumes. And it turns out this is smaller than we can accurately measure by hand, right? So we have nice low volume syringes in the microliters, that's easy, but really getting down to low nanoliter volumes and doing it reproducibly, right? That's an important part. You want every injection to have a similar volume. It can be extremely difficult. In fact, it definitely is extremely difficult. So you need automated methods to get to these kind of small volumes. That's actually the basis of a whole field of research that I'm hoping we'll talk about soon called microfluidics. So the way that you do this, the way that you get down to these really small volumes is by a technique called split injection. So let's talk about how a split injection works. In a split injection, so the example that we just talked about, I said was called a splitless injection. A little bit more detail on that in a second. But in a split injection, you're actually going to open this valve while you're doing the injection. And what that means is that your gas flow coming in here is going to have two possible paths that it can go. It can go out to waste, or it can go through the column. So the flow is going to literally physically split. If this valve is wide open and there's very low resistance down here, the overwhelming majority, because remember the column is narrow and it's very long, so there's a lot of resistance to flowing through this thing. The overwhelming majority of your sample and your gas flow is going to go out to waste when this valve is wide open and there's low resistance going in this direction. So that's a split injection. You're splitting your flow and most of it goes to waste. But in a split injection, so let's just say the key points here is that the split valve is open and most of the flow is going out to waste. That means that you're really only getting on the order of a few percent, maybe 1 to 2% of total gas flow, including the sample that you've just flash vaporized, enters the column. So you can prepare a sample that is a few microliters in size, and you can get down in here. You can rapidly you can inject from your syringe. You can rapidly flash vaporize. You can rest assured that most of it's not going into your column, so you're not over injecting, but you will get this small amount of flow where a small percentage enters your column. So there's a pro and a con here, right? So the pro is that this is a simple and reproducible route to nanoliter volume injections, right? It's a simple route to nanoliter injections. Here's the big con of this. The big downside is that this is not great for a term we don't use a lot, but makes sense, trace analysis. All this means is when you're trying to analyze the components of the sample that are at very low concentrations, so the trace components, the things that are just barely there. So this is not great for trace analysis, and that's because you're throwing away most of your sample. Right, you're throwing away most of that sample. Excuse my terrible handwriting. And if your goal is to measure something that's barely there in the sample and you're throwing most of that sample away, well, you're not doing yourself any great favors. And so the alternative to this, if you do want to do trace analysis, you do want to maximize the amount of sample that you can actually analyze on the column, is to do the procedure that we originally talked about, the splitless injection. So splitless injection. And this is the concept. It's just the opposite, right? We've talked about it already. It's closing a split valve. So you get 100% sample onto the column. So we've talked then, we can just kind of deduce from what we already said that the major benefit here, the big pro, is that you dramatically increase your sample loading. Which is good for trace analysis. Right, for looking at things that are at very low concentration. The downside, if you want to call it that, is that you need to do this a column with a high sample loading capacity. So these were things like our porous layer open tubular columns or our support coated open tubular columns, things that maximize the volume of stationary phase. And even still, I guess the second con here, it's going to cost you. These things are going to cost you dollar bills, that's for sure. But it's also going to cost you in terms of sigma injection, right? You're starting with a much larger injection plug on that column. You're going to get poorer peak efficiency. Okay, that's everything I wanted to say about the injector and the oven, and we'll talk in the next video here about a few examples of really common detectors in GC and their properties.